Jnanam Paramam Dhyayam. Knowledge is supreme.
All right, so let us continue about the dimension. So first of all, note that as I said, we will use the fact that this polynomial ring in several variables over a field, this is Noetherian. And therefore, any algebraic set V, Vk this is intersection of finitely many hypersurfaces, Vf1 intersection Vk finitely many hypersurfaces. Not only that, this ideal A has a primary decomposition, because in a Noetherian ring every ideal has a primary decomposition. That means this ideal A is written as the intersection of finitely many primary ideals QR, where Q1 to QR these are primary ideals. This is why in fact Noether have proved primary decomposition for ideals in a Noetherian ring, and their radicals are when you say primary ideals corresponding to the P1 to PR are their radicals. These are then one calls this Qi to be Pi primary. And therefore, when you apply V and look at the properties of V, then therefore Vk of A will become V of Q1 intersection QR, but then this will become union. So this will be V of Q1 union V of QR, but these QIs are the radicals are radical of Qi is Pi, and therefore V doesn't depend on the radical, therefore this will be V of P1 union V of PR. Therefore, if one wants to study this, I wrote V, so this is Vk everywhere. Therefore, if one wants to study this V, I have to study this union, and therefore the dimension of this will be the sup, because that was our property 2. So therefore, and also no, this is therefore what we proved is every algebraic set in Kn is a finite union of algebraic sets of type V, K, P, where P is a prime ideal. In the ring Kx1 to Xn, but these are precisely the irreducible algebraic sets. This needs little proof, but I am not going to prove it. You take it as exercise. Therefore, what we have proved is every algebraic set is a finite union of irreducible subsets. All right. Therefore, 2 says, so we have proved therefore V algebraic set is a union of let me call it V1 union VR where these V1 to Vr are irreducible algebraic sets. And therefore, our property 2 says that at least one of them will have the same dimension as V. So, dimension of property says that dimension V should be equal to the supremum of dimensions of Vi's and therefore, this is a supremum over finitely many V1 to Vr and therefore, supremum has to attain. Therefore, dimension of V will be equal to dimension of one of them. Let us say V, let me call it V naught, and this V naught for some irreducible subset of V. If dimension V naught is positive, then the property 4 says, then by property 4 there exists an irreducible algebraic set V1 of V0 proper, so that the dimension drops by 1 such that dimension of V1 equal to dimension of V0 minus 1. That was the property 4. All right. So, therefore, if D was the dimension of V, so therefore, if D is the dimension of V, we continue this argument. So that means we can find a chain, then there exists a chain V0 properly contained in V1, properly contained in VD of irreducible algebraic sets of V, algebraic subsets of V, such that at each stage dimension is dropped by 1, such that dimension of Vi equal to D minus I for each I from 0 to 1 to 0 to D. Conversely, if I have a sequence, on the other hand, given a sequence V0 contained in V1 contained in equal to Vr of irreducible closed subsets of V with Vi, of course, irreducible closed, and part of the irreducible closed is Vi's are not equal to empty sets. Then dimension of V should be bigger equal to dimension of V naught, because all these are contained in V, and at each stage the dimension is dropping by 1. So, dimension of V naught will be at least R. See, this will be drops by 1. So, this at least dimension of V naught will be at least R. This is by the property 2 and 3. So, it is, therefore, we can make the following definition. So, this allows us to make the following definitions. And what is the definition? So, definition. The dimension of an algebraic set V contained in K power n is dim V. This is a definition I am making. Sup of R is in n, such that there exists a sequence V0 contained in V1 contained in VR of irreducible algebraic sets, algebraic subsets of V. That is it. So, dimension is the supremum of the chain of the length of the chains of irreducible subsets contained in V. That is what we come to the conclusion, that dimension should be this, and if we define this, it satisfies the desired properties. Once we have this, and here also note that when we should make this convention, supremum of empty set is -1. This is actually not a convention, but it is a force convention, because if you take an empty set in natural numbers, what is the supremum? We should put that to be -1. So, once you have defined this, it is easy to check that it satisfies the properties 2 and 3. 2, 3, 4. So, now easy to check that this definition has properties 2, 3 and 4. We have only assumed 2, 3 and 4 and come to this conclusion that the dimension should be this one, that is the supremum of the lengths of the chains of the irreducible closed subsets contained in V. And now when I want to translate this to algebraic definition, now how do I translate to algebra? So, translate this into algebraic definition. How do we translate? So, that means I have to translate a chain. So, V0 which is irreducible, therefore, it is Vk of some prime ideal P0, and then contained in V1, V1 is irreducible, therefore, it is Vk of some prime ideal P1 and so on, and then this Vk of prime ideal PR. This chain I have given, they are irreducible subsets of the given V. V was Vk of A. Right? And how do I recover these prime ideals? That is very easy. That is in Null-Standards. Hilbert precisely proved that if I take ideal of this, apply Ik to this chain, we get, what do we get? Ik of this will be radical of A. So, that is A. I am assuming A is the radical ideal. So, when I apply Ik, I get back my A. Now, this inclusion will get reverse. So, this will be contained in Ik of this, that is P0. P0 contained in this, P1 contained in this, contained in PR. And what is PIs? PIs are prime ideals, where PIs are prime ideals in the polynomial ring. So this will give you what is called a Krull dimension of k x1 to xn modulo this ideal A. Because if I call this ring as R, the Krull dimension in the lectures, how did I define? I look at the chains of the prime ideals here and take their lengths and take the supremum. But now the chain has become the reverse way, because our these operators I and V, they are inclusion reversing operations, and therefore I got the definition of a Krull dimension. So therefore Krull motivated by this in general defined what is the Krull dimension of a ring. So let me recall that. So using this, Krull defined more generally Krull dimension of an arbitrary commutative ring. So what is the definition? So definition, let A be a commutative ring then dimension of A is by definition sup R in N such that there exists a chain of length R. So P0 contained in PR of prime ideals in A. This supremum is called the Krull dimension of the ring, because the Krull was the first to define this. And also note that if A is 0 ring, that is equivalent to saying there is no prime ideal there. Therefore, the supremum is taken over empty set. So therefore, in this case one puts dimension of A equal to -1. This is a definition if you want. So all this used the motivation which came from Hilbert-Nullstellensatz. So therefore Hilbert-Nullstellensatz HNS, this is the real cornerstone. This is the cornerstone of algebraic geometry, is the starting point. Alright, so so dimension of with this, therefore dimension of variety, dimension of algebraic set, V algebraic set in k power n, this is nothing but dimension of the coordinate ring of V, that is you take kx1 to xn and go modulo the ideal of V, Ik of V. That is the definition. All right, now having defined this, the question is how do we compute this? This definition of supremum of lengths of the prime ideals. This looks quite complicated. So therefore, can we say that now the definition is, how do we compute this? So later in the course So from this definition, it is not even clear that if I take V algebraic set in k power n, algebraic set, whether the dimension of V is finite or bounded by n. This is not at all clear. Okay, so to do this, what one does is the following. There are two more concepts of dimension, two more numbers. So one is to V. So the property 5. So note that property 5 says that if I have V given, then I can find a hyperplane, hypersurface, so that V intersection H has, if D is positive, if the dimension of V is positive, then I can find a hypersurface so that this dimension drops by 1 and keep doing this. So that means after finitely many steps, I will come so that the dimension becomes 0. That means I can, so H will be, so keep doing this. So H will be given by a single polynomial. So this is V of F, V of F1 and so on. So after D stages, it will come, the dimension will become 0. So that means what? This means algebraically the following. So V has the coordinate ring, that is kx1 to xn modulo A, and this intersection operation means when I go to algebra, it will become ideal generated by the sum ideal. So this will become, so V intersection H1 will, the coordinate ring will be this ring kx1 to xn modulo ideal generated by A and that F1. And this ring has dimension D, this ring will have dimension D minus 1. And we keep doing this, these stages. That means what? That means we can find polynomials F1 to Fd definitely, because it might happen the dimension becomes 0. So at most it can go to D stages. So these are, we can find the polynomials in D polynomials in x1 to xn such that when I go mod x1 to xn mod ideal generated by A and these polynomials f1 to fd, this dimension of this ring should become 0. So note that when the dimension of the ring is 0 means what? So analyze this. Dimension of A is 0 means, that means the only chain should have length 0. That means sup of the chains. So the sup will, this will be equal to 0. That means at most there is only one prime ideal. There is no other prime ideal contained in that. So this means the first consequence is every non-zero, every prime ideal in A is maximal. Because you have a prime ideal P, it itself should be maximal. If it is not maximal, it is contained in the maximal ideal. But then the supremum will increase. So therefore every prime ideal is maximal. So such rings are called Artinian. So dimension 0, dimension A equal to 0 and A Noetherian. These rings are precisely called Artinian rings. So this gives us a dimension, this gives us a definition of Chevalier dimension. This is Chevalier dimension. So what is it for arbitrary um, uh, local ring. So, also in between one should have remarked that if I want to study dimension of arbitrary algebraic sets, I could study dimension at a point, and this means you take the coordinate ring, that is kx1 to xn, modulo that ideal ik of v, and this point will correspond to the maximal ideal. So, localize this at that maximal ideal, because maximal ideals are the last in that chain always. So, therefore, if you want to study this, it is enough to study this, and therefore, that will reduce study of dimension to the dimension of the local rings. So reduce the study to local rings. So that means what? Dimension of A, this is same thing as dimension dimension of A localized at M, where M is a maximal ideal in A. Once you have done this, then you can define Chevalier dimension. Then Chevalier dimension of a local ring, if A is local, Chevalier dimension is the infimum. So that is also denoted by SA. This is by definition infimum of R such that there exist A1 to AR elements in the maximal ideal M of A, because A is local with maximal ideal M, such that A mod, if I go mod A1 to ideal generated by A1 to AR, this ring is Artinian. We know this thing exists because we have proved it for algebraic sets, that we have such cut successively by the Harper surfaces by using the property 5, and therefore the Chevalier dimension exists. And then one proves the dimension theorem says that the Krull dimension equal to Chevalier dimension equal to degree of the Hilbert-Samuel polynomial. So this is what precisely the dimension theorem. This is proved in the lectures. So I will not repeat what is the definition of a Hilbert-Samuel polynomial, etc. But this gives a fairly good idea of a dimension concept. So couple of remarks here, that we know dimension of a field. So some examples. Dimension of a field K, this should be 0, because the only prime ideal is 0 and nobody else. So therefore the sup is 0. Dimension of a PID, dimension of Z is 1, because the chain is 0 is the prime ideal, and then ideal generated by the prime number, that is prime ideal, and that's all, no more, because non-zero prime ideals here are maximal. So the dimension of Kx is also 1. Also, if I take the power series ring over a field in one variable, that dimension is also 1, because it is a PID. In fact, this is a better PID than this. So similarly, dimension of the polynomial ring, this will correspond to dimension of Kn, which is n, and so on. Now this dimension theorem will allow us to compute dimension of more rings, and also it shows that dimension of a local ring is always finite, because, so this is for a local ring. Noetherian local, because it's a degree of some polynomial and therefore it is finite. And normally in all these subjects, especially commutative algebra, one usually assumes the rings are Noetherian, because it is not worth studying so much non-Noetherian rings, because they do not correspond to any geometric objects. Therefore, one usually assumes the rings are Noetherian, and with this I will stop this lecture. Thank you very much.